There is a moment, if you have ever sat on a bench in any city, when a pigeon lands near your feet. It tilts its head, looks at you with that small, sideways eye, then walks away in that rhythmic, forward-bobbing way, as if it has somewhere important to be. And you think nothing of it. Most people think nothing of it. Pigeons are just part of the background. They live on ledges. They gather near food carts. They cluster on railway platforms and scatter when trains arrive. They are urban furniture, something you step around without looking down. But here is the thing. That bird near your feet may have traveled further this morning than you will travel all week. It may have crossed rivers, highways, industrial zones, and outer suburbs, alone, at altitude, with no map, no GPS, no signal of any kind, and found its way back to within a few meters of exactly where it started. And it did this with a brain smaller than your thumbnail. There is something happening inside the pigeon that science is still, even now, struggling to fully explain. And the more scientists study it, the more it stops feeling like animal behavior and starts feeling like something else entirely. Something that makes the city you think you know look completely different. For most of human history, the pigeon was not ignored. It was revered. Ancient Egyptians used them to carry messages. Persian kings maintained vast lofts of trained birds. During the First World War, a pigeon named Sher Ami delivered a message through active gunfire, already wounded, leg nearly severed, and saved the lives of nearly 200 soldiers. He was awarded a medal. But that was before phones, before satellites, before we had our own navigation systems. Once we built machines that could do what the pigeon did, we stopped paying attention to how the pigeon did it. We assumed it was instinct. Simple instinct. The way we assume a compass points north because that is what compasses do, without wondering at the invisible force making it happen. We looked at the pigeon and saw an ordinary bird. We were not even close to right. The first serious scientific attempts to understand pigeon navigation began in Europe in the mid-20th century. Researchers would take birds from their home lofts, drive them to release sites they had never visited, sometimes hundreds of kilometers away, and watch what happened. What happened was difficult to explain. The birds would circle once, sometimes twice, get their bearings, and then fly home. Not approximately home. Not in the general direction of home. Home. The actual loft. The specific building. The exact rooftop. Scientists tried releasing them in fog. The birds still oriented correctly. They tried releasing them under heavy cloud cover, when no sun was visible. The birds still found their way. They released birds in featureless, flat terrain, no rivers, no coastlines, no visible landmarks of any kind. The birds still flew home. One researcher, trying to understand what the birds were using, placed small magnets on their heads to disrupt any magnetic sensitivity. The birds became disoriented. Remove the magnets, and they recovered. That was when things became genuinely strange, because it suggested the pigeon could feel the Earth's magnetic field, not just as a vague pull, but as navigational information, as a kind of internal map. Here is what that actually means. The Earth is wrapped in a magnetic field, invisible lines of force that run from pole to pole, bending and curving across the surface of the planet. We cannot feel this field. We have no sensory organ for it. To us, it is as invisible as ultraviolet light, as silent as a radio wave. The pigeon may feel it. Inside the beak of a pigeon, researchers found clusters of cells containing magnetite, tiny iron-based crystals that respond to magnetic fields. There is evidence that these cells may act like a biological compass, sensitive enough to detect not just the direction of magnetic north, but the intensity and inclination of the field, which changes depending on latitude. That means the pigeon may be able to derive, from the feel of the magnetic field alone, an approximation of where it is on the Earth's surface. Not which street, not which city, but a coordinate, a position. Something like, I am south of where I should be, and I need to go north. No device, no signal, just cells, crystals, and a magnetic field that has been wrapping the Earth for billions of years. But that is only the beginning. Pigeons also navigate by the sun. This sounds straightforward until you think about what it actually requires. The sun moves. It rises in the east, arcs across the sky, sets in the west, and its position at any given moment depends on both direction and time. To use the sun as a compass, you cannot just look at where it is. You have to know what time it is, compensate for the sun's movement, and calculate direction from both pieces of information simultaneously. Pigeons do this. They carry an internal clock, a circadian rhythm so precise that researchers who shifted the light-dark cycle in a loft, gradually convincing the birds that noon was actually 6 in the morning, found that the birds released outdoors flew in systematically wrong directions. They had compensated for the sun's position, but using the wrong time, and so their calculations were off. This is not instinct in the simple sense. This is calculation. The bird is doing something functionally similar to what a ship's navigator does with a sextant and a chronometer, measuring the position of a celestial body against a known time to determine direction. The pigeon is doing this without hands, without instruments, without being taught. It is doing it with the machinery of its own biology. But take the sun away. Cover the sky completely. Researchers who expected this to stop the birds found it did not always stop them. Some birds, even under total overcast, oriented correctly. Not all of them, and not as accurately, but enough to suggest that something else was also operating. Some researchers began looking at infrasound. Infrasound is sound at frequencies far below what humans can hear. It is generated constantly by the earth, by ocean waves, by wind moving over mountain ranges, by pressure changes in the atmosphere. These sounds travel enormous distances, bending and bouncing off geographical features in ways that could, theoretically, be used as a kind of auditory map. A mountain range produces a particular infrasound signature. A coastline produces another. A city generates its own low, constant frequency hum. There is evidence that pigeons can hear these sounds. If they can, then even in fog, even at night, even with the magnetic field disrupted, a pigeon might still be listening. Building a picture of the landscape from sounds no human can hear. Hearing the shape of the world below. And then there is something even stranger. Something researchers in Italy discovered that changed the entire framework of how pigeon navigation is understood. They found that pigeons may also use smell. Not smell in the way we usually mean it. Not following a scent trail on the ground. Something more radical than that. The theory goes like this. Air carries chemical signatures from the places it has passed over. The sea leaves a particular chemical composition in the air. Forests do the same. Industrial zones. Agricultural land. Urban centers. Each landscape contributes its own trace of chemistry to the moving air. Wind direction determines which way these chemical signatures travel. If the wind at your home loft comes predominantly from the southwest, the air that reaches you from the southwest carries the scent of whatever landscape lies in that direction. Over months of living in a loft, a pigeon may build what researchers call an olfactory map, a mental image of the world constructed entirely from smell. Not what things look like, but what the air smells like depending on where it comes from. When released far from home, the bird smells the local air, identifies which chemical signatures are present, compares them to its internal map, and calculates. This is what the air smells like when it comes from the northeast of my loft. Therefore, I am to the northeast of home. Therefore, I fly southwest. Researchers who destroyed the olfactory cells in pigeons found that the birds lost navigational ability dramatically, especially when released in unfamiliar territory under overcast skies. The pigeon was smelling the direction home. What makes all of this feel almost impossible is not any one of these abilities on its own. It is that the pigeon appears to use all of them at once. It does not rely exclusively on magnetism, or the sun, or infrasound, or smell. It integrates all of these inputs simultaneously, weighing each one against the others, defaulting to whichever system is most reliable given the current conditions. If the sky is clear, lean on the sun. If clouds move in, shift toward magnetic sensation. If the magnetic field is disturbed, cross-reference with smell. If all else fails, listen to the landscape. This is not how a simple animal behaves. This is how a sophisticated system behaves. A redundant, adaptive, self-correcting navigation system with multiple independent inputs and the ability to weight and balance them in real time. Engineers who design navigation systems for aircraft and spacecraft use exactly this same principle. They call it sensor fusion. They build it deliberately, at great expense, with considerable complexity. The pigeon was born with it. Now think about the city. The city you walk through every day. The streets you know by name. The buildings you recognize. The routes you take without thinking. You navigate that city through a narrow slice of reality. Eye level. Ground surface. street signs, your phone. Above you, right now, there are pigeons navigating the same city through an entirely different layer of reality. They are reading the magnetic inclination of the field passing through the buildings below them. They are calculating the angle of the sun against an internal clock accurate enough to serve as a compass. They are listening to the low-frequency sound of the city itself, the hum of infrastructure, the acoustic signature of the skyline, and comparing it to what that hum sounds like from home. They are looking down at the railway lines and roads and rooftop patterns and recognizing them as landmarks in a map they have built across years of flight. Every route they have ever taken is encoded somewhere in their memory, available to be retrieved and integrated into the current journey. The rooftops you pass under every morning without looking up, to a pigeon, they are a topographic map, a network of recognized landmarks as clear and precise as road signs are to you. The urban sky that looks like empty space from a street corner is threaded with invisible paths, routes defined not by roads or rails, but by the accumulated navigational experience of generations of birds that have crossed the same corridors of air, over the same landmarks, through the same magnetic and acoustic landscape, for as long as cities have stood. There is a version of your city that exists above you, that you cannot see, cannot feel, and cannot access. The pigeon lives there. What scientists keep returning to, what the data keeps suggesting, is that we have significantly underestimated what is happening inside the pigeon's mind. The brain is tiny. This is true. But the pigeon's hippocampus, the region associated with spatial memory and navigation, is proportionally very large. Birds that navigate complex territories have larger hippocampal regions than birds that do not. In the pigeon, this region is dense with neural architecture devoted to spatial processing. The bird is not doing something simple. It is doing something that requires memory, calculation, sensory integration, and real-time decision-making across multiple simultaneous inputs. And it is doing it every time it flies home. The pigeon on the ledge outside your office window, the one you have walked past 100 times without a second thought. That bird may have completed navigational journeys that would challenge a trained pilot without instruments. It may be carrying, inside that small gray head, a map of this city more detailed and multidimensional than anything drawn on paper. It has found its way home across fog and rain and disrupted magnetic fields and unfamiliar territory, and it has done this without asking for directions, without reaching for its phone, without any of the external infrastructure humans require to navigate even a new neighborhood. There is something unsettling about this when you sit with it long enough. Not unsettling in a frightening way. Unsettling in the way that all genuine discoveries are unsettling. The way it feels when the thing you thought you understood turns out to be much larger and stranger than you believed. We share our cities with these birds. We have shared them for centuries. They walk across the same squares we cross. They watch us from the same ledges where they have always watched. And the whole time, they have been operating inside a sensory reality so different from ours that we might as well be living in different worlds. We look at a gray sky and see cloud cover. The pigeon looks at the same sky and reads magnetic field intensity, calculates solar position, hears infrasound frequencies from the landscape below, and smells the chemical signature of home on the prevailing wind. We were looking at the same sky. We were seeing almost nothing at all. The next time a pigeon lands near you, on a bench, on a station platform, at the edge of a market square, take a moment. Just a moment. Look at that small eye. That unhurried tilt of the head. That bird knows where it is. It knows where it came from. It knows, with a precision that still surprises the scientists who have spent their careers trying to understand it, exactly how to get back home. It has always known. We just never thought to ask how.